Okay, so in this podcast we're going to talk about calorimetry, which is a method that scientists use to figure out what the change in energy is during a chemical reaction. And tomorrow we're going to do a lab using this method, using the more crude version of the method. Now, we jumped ahead a little bit, and we're going to talk about this before we've really talked about the term enthalpy. But what I ask is that you trust me when I say Q, which is, first of all, we're going to deal with the reactions where there's no change in volume. They're open to the outside, right? So they're not a closed system, and because of that, there's no change in volume. So the change in energy is Q, just Q. There's no W, right? And eventually, we're going to see this term delta H, which means stands for enthalpy. And for right now, what I want you to know is that enthalpy, when we have something where there's no work, a system where there's no work involved, just heat, delta H and Q are the same. So we're really talking about Q here. Okay? So we can measure Q. We can measure the energy or the heat involved in the chemical reaction through this process called calorimetry, where we're really measuring the change in heat. Okay, so let's take a look. First, let's talk about a couple terms. We talk about heat capacity and specific heat, and every substance has its own heat capacity and specific heat, and you can find these as published values on the internet or on your textbook. But the amount of energy required to raise the temperature of a substance by 1 degree Celsius or 1 K, which is the interval size. If I have 10 C, it is 283 K, right? If I have 11 C, this degree C, is 284 K. So the change in 1 C is the same as the change in 1 K. So if I increase it by the amount of energy required to increase the temperature by 1 degree is called its heat capacity. Okay? And you can see the heat capacity for a variety of substances. Here are published values, different elements, different compounds. And one of the things that you can see here is water's value is the highest on this list. We'll talk a little bit more about that. So specific heat, we were just talking about heat capacity. Specific heat capacity is has a mass element to it, and we call this C, and it's usually called just specific heat. I'm trying to get my bearings straight. I'm sorry, I'm drawing crooked lines. As the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree K or degree C. Okay, so the difference between heat capacity and specific heat capacity is this has the mass component to it. This was just the amount of heat required to raise the temperature 1 degree C or 1 K, right? This is to raise the 1 gram of substance 1 degree C or 1 K. Okay, so again, same table here. This specific heat for water, very high. Now this should be a review from Honors Chem. You should have learned this in Honors Chem. Specific heat is defined as this value C, and it's the heat transferred over the mass times the temperature change. And we rewrote that last year as Q equals the mass in grams. This is going to be in grams times C, which is the specific heat capacity, times the change in temperature. Now you've got to be careful with your units, because sometimes C will be given to you in joules per gram, and therefore this is going to be grams here. But sometimes your C will be given to you in joules per mole. Okay? And if that happens, then this is going to be moles. So you have to just look at your units, right? If it's grams, you want grams here. If this is moles, you want moles here. Okay. So Q is the heat that's being transferred. second. M is the substance's mass in grams. C is the specific heat capacity, and the units are kind of funky, right? They're joules per gram degrees C. And then there's a change in temperature, which is, of course, going to be in K or C. Okay. So when you do that, what you end up with is grams for the mass times this C, which is joules per gram degrees C, times your change in temperature, which is C. And what happens when you set up those units is the grams cancel, the degrees C cancel, and you're left with just joules. That's why the units are funky on the C. Okay. Now, the specific heat of water you will use a lot, so you'll get to know 4.18 joules per gram degrees C. Okay? And it's a really high value, and that, if you look at the value for water here compared to other substances, really high for liquid water and water vapor compared to things like air, wood, metal, really low. And that means that in order to raise a gram of water by 1 degree C, it takes a tremendous amount of energy. A lot easier to raise the temperature of iron or wood. Takes a lot less energy. Okay, so water has a very high specific heat capacity. And that's why the old saying, a watched pot never boils, is kind of true. It takes a really long time for a pot of water to boil because it's got a very high specific heat capacity. It needs a lot of energy to get that to boil. And more importantly, it also really controls the weather. So our oceans are pretty moderate in temperature, because we can have pretty wide swings in air temperature, and the water does not change appreciably in temperature, right? So a lot of energy can come and not cause the oceans to heat up excessively. But it also, all that energy that would only raise the temperature a relatively small amount is still a lot of energy in that water, which will lead towards things like hurricanes. And you often hear that the water, the ocean, provides the fuel to feed the hurricane, right? So it doesn't take much water to, because it has a lot of heat, built up heat, to really affect the weather. So there's lots of things about water that are really special and really neat, and a lot of it is because of its special high specific heat capacity. Now the key idea of calorimetry is that the heat lost by a metal is going to be the heat gained by water. So this is the idea. So I take a piece of metal and I heat it up, right? Get it really hot. And first I find out what the temperature of the metal and the water is. And it's good to do something like this after you've let the materials sit out. So you're pretty sure they're going to be at the same temperatures. Maybe have them sit out overnight. You heat up this, let's say this piece of metal, and you then put it in the water and you measure the change in temperature. And that change in temperature allows you to determine for water, because you know what the mass of the water is, you know what the heat capacity of water is, 4.18 joules per gram degrees C, and you know what the temperature change is, you can calculate the heat that went into the water. So the heat that went into the water is going to be the same, just opposite direction of the heat that was lost from the metal. Okay? So the key thing is the heat lost by whatever you're putting in the water is equal to the heat gained by the water. And we can actually calculate the heat gained by the water. So let's take, say I take this hot metal, heat it up to close to 100 degrees C. I put it in this water that's been sitting out at room temperature. I immerse it, causes the water to rise in temperature from 21 degrees to 23 degrees. Metal cools in this exothermic process. The change in temperature of the metal is negative, the change in temperature of the water is positive, right? So we can figure out how much energy was involved in making that change of the water, and that's going to be equal to the change in energy involved with the piece of metal. Okay, so we call this constant pressure calorimetry, and we use what's called a coffee cup calorimeter. Pretty crude, but it works remarkably well. You have some heat loss, but it's not too bad. Typical setup, and we're going to do this in the lab, is you take two styrofoam cups that are nestled together. And styrofoam is a great insulator, so there's not a lot of heat that will leave through it. You have some type of a lid that's not, you're going to try not to lose a lot of heat, but it's not securely on there, so it's really still constant pressure. If this gas is building up, they're going to get out. And then you measure the change in temperature. Okay? So this is a pretty simple calorimeter that we will use in the lab to figure out what's going on with the specific change, be it physical or chemical. Okay, and because we know the specific heat for water, right, this value that we're going to know, we can measure the change in enthalpy, which is also our Q, using Q equals MC change in T. Now there's also a more sophisticated type of calorimeter called a bomb calorimeter. And if you, as you can imagine, this is going to be a calorimeter that's completely closed. Oops. And so it's in a strong metal chamber. There is a couple of electrodes that will be used to spark the reaction to begin. There's still a thermometer. You stir in the water. Okay, but there's actually a reaction chamber, and it's not open to the outside, so it's not constant volume. But it is constant pressure. Okay, the pressure can't change in here. So again, the heat absorbed by the water is a good approximation for the enthalpy or the heat, the Q change, right? Because the volume in the bomb calorimeter is constant, what it's really measuring is the change in internal energy, okay, delta E. Now, for most reactions, and we'll talk a lot about this later in this unit, delta E and delta H are pretty much, for most reactions, the same thing. Very, very close. So let's take a look at a real problem. Okay, so here I have a coffee cup calorimeter, and I have 100 milliliters of 1 molar sodium hydroxide, 100 milliliters of 1 molar HCl, and both solutions originally are at 24.6 degrees C. After the reaction, the final temperature is 31.3. Assuming all the solutions have a density of 1 gram per centimeter cubed and a specific heat of waters, which is what we know, right? Calculate the enthalpy change for the neutralization of HCl by NaOH. And assume that no heat is lost to the surrounding. That's a big assumption, and there will be some loss, but we're going to assume that there's none lost. Okay, so what we want to do is take a look at what we've got. Okay, so we're going to use Q equals M times C times change in T. So let's talk about mass. We're not given the mass of what we're putting in here, but we are given the density, right? So we have two solutions. They are both 100 milliliters, and what we're saying is this is 1 gram per centimeter cubed. Okay, so the density is 1 gram per centimeter cubed, and I have 100 plus 100, 200 milliliters, right? Which is the same as centimeters cubed. So the centimeters cubed will cancel out, and this is going to be 200 grams, right? 1 gram is 1 centimeter cubed. I've got, would you agree, I have 200 grams if my density of that material is 1 gram per centimeter cubed. So I have 200 grams. My heat capacity is 4.184 joules per gram degrees C. Now this is for water, and we're looking at what's happening to the water, okay? Times my change in temperature, which is 31.3 minus 24.6, which is 6.7 degrees C. Okay, and if I multiply that out, I'm going to cancel my grams, I'm going to cancel my degrees C, I'm going to end up with 200 times 4.184 times 6.7. My calculator says 5606.56, and looks like I have 4 sig figs, 4 sig figs, 2 sig figs, so I'm going to go with 2. So I'm going to call it 5600 joules, which I could also say is 5.6 kilojoules. Okay, not so bad. Let's take a look at this one. Alright, so we're going to again talk about delta H enthalpy. It's really, let's think about it same as we would with Q. So it says we have 1 mole of methane, right, that is burned at constant pressure, so that means there's no work, right? 890 kilojoules per mole is released as heat. Calculate the delta H for a process in which a 5.8 gram sample is burned. Okay, so I have 890 kilojoules per 1 mole, right? And here I have a 5.8 gram sample, so I got to figure out what percentage of a mole that is. So this is CH4, so carbon is 12.01, each hydrogen is 1.01, so that's 4.04, so that's 16.05. So if I have 5.8 grams and the molar mass is 16.05 grams, and I punch this on my calculator, I get 5.8 divided by 16.05, and I get 0.3614 moles, right? And I multiply that times 890 kilojoules, and I get 322, I'm going to call it 320 kilojoules in that small sample. Okay? Just an easy stoic problem. Not even stoic, just factor label problem. Alright, let's take a look at one more. So we have 1 liter of 1 molar barium nitrate at 25 degrees C. It's mixed with 1 liter of 1 molar sodium sulfate at 25 degrees C. And a white solid is formed, and the temperature of the mixture increases by 28.1 degrees. So I know the change in temperature is 28.1 degrees C. Assuming that the calorimeter absorbs only a negligible quantity of heat, and the specific heat is 4.184 joules per gram degrees C, and the density of the final solution is 1.0 grams per milliliter. We want to calculate the enthalpy change per mole of barium sulfate that's formed. Okay, so we need to do a little stoic and just make sure we know what we got. So we've got barium nitrate plus sodium sulfate. They will make barium sulfate, and sodium nitrate will have 2 of those. So for every 1 mole of this and 1 mole of this, I get 1 mole of barium sulfate. So let's see how many moles of this I have. I have 1 liter of 1 molar, and because molarity is moles over liters, moles is molarity times liters, and here I have 1 liter times 1 molar. That's going to be 1 mole. This is 1 mole. I get the same thing here. I also have for the 1 liter of 1 molar sodium sulfate. So I'm going to say this is 1 mole. So I'm going to get 1 mole of this. Okay? Alright, so let's plug this into Q. Q equals M times C times change in T. Okay? So my M is, I have 1 liter plus 1 liter, so I have 2 liters, which is 2,000 milliliters, and because it says the density is 1 gram per milliliter, I also have 2,000 grams. Okay, so I have 2,000 grams times my heat capacity, joules per gram degree C, and my change in temperature is going to be it went from 25 to 28.1, and that is a difference of 3.1 degrees C. My C's cancel, my grams cancel. If I plug this in, I'm going to end up with looks like 26,000. Looks like I want 2 sig figs. So 26,000 or 26 kilojoules per mole. So what's the enthalpy change per mole? So that looks like that's what it's going to be, 26 kilojoules. Now, the change in enthalpy, this is going to be, let me see, the temperature went up, so this is going to be an exothermic. It's going to be a negative. Alright, let's try another one. Alright, it's been suggested that hydrogen gas obtained by the decomposition of water might be a substitute for natural gas. To compare the energies of combustion of these fuels, the following experiment was carried out using a bomb calorimeter. So for a bomb calorimeter, it's not going to be Q equals M times C times change in T. It's going to be C times change in T. Okay? So to compare the energies of these, alright, the heat capacity is 11.3 kilojoules per degree C. Okay? We have a 1.5 gram sample of methane. When burned with excess oxygen, temperature increased by 7.3. Okay, so with methane, CH4, temperature went up 7.3 degrees C. Okay, and that was a 1.5 grams of methane. Okay. And then for hydrogen, we have a 1.15 gram sample, and our change in temperature is 14.3 degrees. Alright, so we want to compare the two. So Q equals, and we're not going to use mass in here, right? We're just going to use C times T. So it's C times change in T. So for methane, for CH4, Q is going to be 11.3 kilojoules per degree C times the change in temperature for methane, which was 7.3 degrees C. And this is going to come out to be, looks like 82.5 kilojoules. Okay? And I want to compare gram per gram. Methane used 1.5 grams, okay? So if I divide that out, I'm going to get 55 kilojoules per gram of methane, okay? I'm going to do the same thing with my Q for hydrogen, is equal to C times change in T. My C is the same. It's what the calorimeter provides, kilojoules per degree C. And my temperature change here was 14.3. Okay, my degree C, I cancel out my C, and I end up getting, let me see, that's going to be, looks like 161.5, oops, kilojoules, and this is per 1.15 grams, right? So that's going to come out to be 140 joules, whoops, per gram of hydrogen. Okay, so actually this is kilojoules, right? So it looks, let me rewrite that, 140 kilojoules per gram of hydrogen. So it makes it look pretty attractive. It looks like it's almost 3 times as much energy per gram as you get from methane. Now there's probably a lot of other factors you need to consider, but from an energy per gram, hydrogen gives you more bang for your buck. Alright, so we're going to stop there, and tomorrow we'll do a lab using calorimetry.